हेलो दोस्तों, कैसे हो? मेरे इस YouTube चैनल में आपका स्वागत है। तो चलिए शुरू करते हैं। Now we'll see design considerations in casting. Now understand the meaning of the topic. The topic is whenever you are designing a product that will be casted, मतलब casting से बनेगा वो product. Okay. Then what are the factors that you have to consider फ्रॉम डिजाइन पॉइंट ऑफ व्यू? डिजाइन मतलब उसका लोकेशन कैसे होगा, उसका डायमेंशन कैसे रखना है, ऑल दिस पॉइंट्स विल कम व्हेन यू आर वी आर थिंकिंग अबाउट डिजाइनिंग अ पार्ट टू बी कास्टेड विच इज टू बी कास्टेड। ओके, तो इस टॉपिक का मतलब ये है कि कास्टिंग करना है तो मुझे क्या सोचना पड़ेगा। मैं डिजाइन इंजीनियर हूँ और मुझे कास्टिंग का प्रोडक्ट डिजाइन करना है तो मुझे क्या सोचना पड़ेगा। दिस इज द मीनिंग ऑफ दिस टॉपिक। सो व्हाट इज द फर्स्ट कंसिडरेशन? You have to design the cast part. So first consideration is design parts to be in compression than in tension. I told you casting is brittle. Casting is made up of cast iron. Cast iron is brittle material. And if you remember, I told you cast iron has excellent compressive strength. Cast iron is strong in compression, and since it is strong in compression and weakest in shear. Now since it is strong in compression, it can absorb all compressive forces, and when we are applying any tensile force on it, then it may fail because of tension. So all the machine parts, all all the lathe machine, milling machine, all those parts are made up of casting. Why? Because it has to absorb all the vibrations, all the forces which are created during machining. So cast iron is the best material. And second thing is the parts are intricate in shape. ऐसे नहीं है ना सिंपल शेप रहता है। बेस का शेप कैसे रहता है? थोड़ा इंट्रिकेट रहता है। इधर से बाहर से कॉर्नर निकला हुआ है, फिर इधर से वो तिरछा है, समथिंग लाइक दैट। इट इज नॉट अ कॉमन रेक्टेंगुलर प्रॉपरली डिजाइंड शेप. इनफैक्ट इट इज डिजाइंड बट इट इज नॉट दैट रेक्टेंगल. So it is easy to be casted. So what is written here? Design parts to be in compression than in tension. So whenever you are designing a part, किस पार्ट का डिजाइन कर रहे हैं? ब्रिटल मटेरियल, कास्ट आयरन, जो कास्टिंग से बनने वाला है. सो यू हैव टू डिजाइन इट इन टू बी इन कॉम्प्रेशन. यू डिजाइन इट इन सच अ वे दैट द पार्ट विल बी इन कॉम्प्रेशन एंड नॉट इन टेंशन. ओके, सो यू मस्ट थिंक, यू मे बी थिंकिंग कि जहाँ पे टेंसाइल फोर्स अप्लाई करना चाहिए वहाँ पे कॉम्प्रेसिव फोर्स अप्लाई करना, ऐसे हो गया वो. Yes, it's that way exactly. Instead of applying tensile force, you have to apply compressive force, but you have to you should get the same result. You should get the same result in tension as well as compression. So what you have to change? You have to change the location of the force. Okay, we'll see it in the sketch. First, I will read this. Cast iron is much stronger in compression than in tension. Hence, design the parts such that stressed area of the parts are under compression rather than under tension. So instead of a part being in tension, you design it such a way that it is in cast compression. Now you can see here. This is a bracket, and this is subject to tensile force here. Pull force, tensile force. It will create tensile stresses. And if it is a if it is a casted part which is to be produced by casting, then this is a poor design. So what I said, instead of tensile force, make it compressive force. You can see here it is pulled in downward direction. So pulling in downward direction is tension. So pushing in downward direction will be compression. See, like this. Okay, so depending on how you want it, this force could have been in upward direction, or force could have been acted in upward, this from here in downward direction. Okay, so instead of designing the part to be in tension, now this part is in tension and this part is in compression. Okay, if the sole purpose is that the entire part should remain in compression than in tension. Then second design consideration is strengthen parts under tension by use of external devices. Now every time every time it is not possible to change the tensile nature of the force to compressive nature. Okay. Sometimes it is possible by changing the orientation of the point, changing the position of the point of application of the force. or changing the point of application of the force. It is possible. Every time it is not possible. So in such case, what will we do? When tensile stresses are unavoidable, consider a clamping device such that the tie rod or such as a tie rod or bearing cap. This will strengthen the part. For example, this. You can see this force P and this force P. What is it doing? It is applying tensile force on this. तो ये टूटेगा कहाँ से? It will break from here. Okay, you can see it will break from here. And it is not possible to apply compressive force. अंदर से मटेरियल को कैसे खींचेंगे? इसको मटेरियल के अंदर से नहीं खींच सकते ना. And even if you apply force from this side, then also it will be tensile, which may not be required, which may not be the requirement of the design. But what we have to understand here is the force applied here is tensile, and we cannot convert it into compressive. Then a better design is provided here. See, force applied is still tensile, it is still tensile, but then this clamping device that is used in the form of a nut and a bolt, what it is doing? It is holding this part as well as this part. It is holding both the parts, and since it is holding both the part, what happens? This part and this part will not easily fail from here. Will not easily fail from here. It can fail. It may fail from here. It may fail from here, but not that easily. As easily, this can fail. Or there is another way to use I will not say nullify, but to reduce the effect of this tensile force. This is one way, one method, and this is second method. Now you can see a bearing cap is provided here, because of which what will happen? The force which is applied by this, whatever is there to apply the force, will be taken up by this, and it will be taken up by this. So now this is not vulnerable as it was here. It's not that vulnerable to suddenly fail because of tension or tensile force. Okay, so first is to design, as far as possible, design the parts in compression. Second, if it is not possible to design the part in compression, what you can do is you can provide some additional support. You can provide some additional support. So these are the two things. Then the third is you have to round all external corners. Whatever corners are there in the part to be designed, you have to round it up. Round it up means how can you round it up? Suppose this and this is the part to be designed. So instead of design it like this, design it in such a way that the corners are rounded. Corners are rounded, and because of this, what will happen? It increases the endurance limit of the component. It increases the endurance limit of the component, and it reduces the formation of brittle chilled edge. So this will be clear in this sketch. See, this is the first case where we have corners. This is a corner, this is a corner. Now understand that this part is made by casting. Casting is there will be somewhere runner there will be runner somewhere through which material will be poured, and the material will slowly go like this. It will go like this. Okay, and when you see when it is poured from here, it will be evenly distributed here. It will be evenly distributed here, and this corner will be the last to be filled. So it may create brittle edge. The edge may be brittle here. This thing. What is another way? Another way is so one way to overcome this is to provide the round or fillet here. Round or fillet. In this case also, and here also you can see a round or fillet is provided. See now, when the material is poured, what will happen in this case? When the material is poured, it will go and this entire thing will fill. Now here somewhere this part is the area is maximum here, since it is tapered surface, inclined surface. If I see this cross section, The area is maximum. Now since the area is maximum, it will take more time to solidify as compared to this or this area. Okay. If it takes more time to solidify here, what will happen? A shrinkage cavity can be developed. You can see here, shrinkage cavity like this can be developed, and then it will not be homogeneous. So in order to reduce this effect, what you can do is to make this circular. Now you can see this area is uniform throughout. Even if I consider this, it is uniform throughout as compared to this point to this point. This is maximum and this is not maximum. This is evenly distributed now. So this is the effect of rounding all the external corners. There is one more benefit of that, and that is stress concentration. Okay, I will come to this point. It is point number 5. So what are the 3 points which we have seen up till now? First point is you have to design the parts to be in compression, then in tension as far as possible. Change the orientation and make the force compressive instead of tensile. Second is strengthen the part by providing some support. This way or this way you can provide the support to the parts which are in tension. The third factor that has to be kept in mind while designing the parts which are to be casted is make the edges round. Make the edges round instead of keeping it corners. Make it round. So this will prevent formation of some cavity where the cooling will be at the end. सबसे लास्ट में कूलिंग जहाँ पे हो सकता है ऐसे जगह पे कैविटी फॉर्म होगा. So that will be prevented. Then fourth point that has to be considered when you are designing the part which is to be machined, which is to be casted is held uniform section throughout, held uniform section thickness throughout. So you can see here, this is a part. This is saying, it is saying that this is a poor design. Now this is a good design. Why it is good? You can see instead of corner here we have a curved shape. Similarly here also, here as well as here, and even here and here, it can be improved. So now you can see instead of this first, second design, the third design is better and the fourth one is the best. So there are less chances of stress concentration in this case as compared to other 3 cases. If you have forgotten what exactly is stress concentration, let me explain you. See, these are the stress flow lines. If this is the material, and it is subjected to some pull force in this direction and this direction, then because of that there are some imaginary stress lines formed, as you can see, like this. These are the imaginary stress flow lines. It means that the stress is flowing like this. Now since the stress is flowing, what is happening? This is uniform now. You can see this is uniform. But instead if I cut here and cut here the material, now these stress flow lines which we are going straight, now they will go like this. The bottom stress flow line will go like this. Then this will go like this. And see what is happening here. At some place there will be congestion. You can see there will be congestion. Where is the congestion? The congestion is here. Similarly, if I draw more stress lines like this, this is the portion where there is most congestion, and this will fail. This will fail from here. This will fail from here. But then that can be improved by doing the change in the shape. Is more better, and this is the best. If the design permits, then that can be done. Okay, next is avoid stress concentration of the metal at the junction. So you can see here. Now as I explained in the earlier slide, somewhere here, this is the part which will solidify at the end. सबसे end में solidify होगा. उसी तरह if it is like this, here also, this is the part which will solidify at the end, and here also there can be formation of shrinkage cavity. So same thing is written here. Whenever there is concentration of metal, the metal on the surface solidifies first, whereas the central portion solidifies much later. This will produce the shrinkage cavity in the central portion That's what I have explained here. Now this can be avoided by two ways. The first way is you can remove this material at the center. इसको material को ही निकाल डालो. If it is possible that you can remove the material from the center, and to increase the strength, what is done? To increase the strength, it is given this shape here. Means some material that was removed from the center is added here. You can see in this sketch, it is added here. Okay, so the overall strength does not reduce this, but then the formation of shrinkage cavity will not take place here. Or second way is to by providing the offset. See, this is vertical, it is kept vertical. Is it necessary that this and this should be aligned? If it is not necessary, then you distribute it upward and downward. So that is called a staggered rip. It is staggered. Okay, so that way what is happening? That way, see, all this part will be uniformly cooled. It will be uniformly cooled, and because of that, there will not be any we can say defect or problem that is created because of the pouring of the casting or after pouring of the casting during the solidification. Okay, so what are the steps we have seen? Once again, let us see. We have to design the part in compression, then in tension, if possible. If it is not possible, then provide some support so that the parts will not fail in tension or not fail that easily in tension. I cannot say that it will not fail, but then its life will improve. Second, now next is round all the corners so that shrinkage cavity will not occur. Then uniform section should be there, or abrupt change in cross sections. Abrupt change in cross section, it should be reduced. And the fifth point that we have seen is avoid stress concentration by providing change in the design. Okay, so this is called as change in design. This is first design, this is second design, this is third design. So you can see that there is certain change in the design. So you have to apply your knowledge. See, this is very good example. Here this material is removed from the core. The material is removed from the core. So overall amount of material that is needed, which will reduce the strength of the part, will be less. Okay, this material is less here. There is no material. So this material which was lost here is added here. See, added here. Where? Here you can see it is added. Okay, here also it is added. So something like this has to be taught. Something tricky has to be thought so that the strength will not be reduced. With the same strength, you have to do some modifications in the design. Though this varies part by part, and this cannot be explained like this. Even though I have given you two examples, but that is not sufficient because every part will have different orientation, and you will have to apply your knowledge when you see the part exactly in front of you. Then only it is possible. But what you have, the next consideration in design is avoid very thin section. Why very thin section has to be avoided? Because when you say thin section, मतलब छोटा, thickness कम है तो क्या होगा? It is brittle material, and brittle material will easily fail. It will quickly fail. That's why if it is thick material, if it is thick like this, if the thickness is more, then what will happen? If suppose crack is initiated here, it will take time to propagate and to reach to the surface, and then it fails into two parts. But if it is a thin section like this crack will easily get propagated and it will fail quickly. So in case if the section is thin, then you have to change the dimension. Change the dimension मतलब देखो, after designing you are getting some dimension. Okay, that is correct, and that dimension says that the material will not fail. But then now I am talking about durability of the material. ठीक है, material आज नहीं fail होगा, लेकिन कभी fail होगा? 8 दिन के बाद, 10 दिन के बाद, after its use of 8 hours, 10 hours, 20 hours, 40 hours. Okay, so that is the question of durability. In that case, what you have to do? See, design value of the thickness is often less. जो डिजाइन करते हो छोटा ही कम मिलता है वैल्यू. It should be increased to practical proportion. You have to increase this value. Minimum section thickness depends upon the process. So you cannot fix what should be the thickness. But there is a rule of thumb that for casting of above 500 mm length, minimum thickness should be about 7 mm. If the length of casting is 500, then minimum thickness is to be 7 mm. If by calculations it is coming as 4 mm or 5 mm, then you have to increase it to 7 mm. Now what are you doing? You are increasing the material, but you are increasing the material at the same time you are increasing the life of the component. So in that case, we can increase the amount of material. And for heavy casting, minimum thickness should be at least 20 mm. Okay. So these are just guidelines, and it says that very thin sections should be avoided. The next consideration, it says that provide uniform wall thickness. Now uniform wall thickness can be explained by this figure. You can see here. This is the first case. So this is part number 1 and this horizontal is part number 2. These two are to be joined. Now these are two separate parts and they have to be separate part based on the maybe the design or something like that. These two has to be separate part. Then what are the ways available with you? Either drill a hole in this and use a screw. Second way is you can use welding over here, or you can use riveting over here, something like this. Okay, so out of which in this particular example, what is shown is a bolted joint or a screw is possible. Use of screw to join or connect this two part is possible. So what is happening in the first case, second case, and third case? The first case, see here, it is very close. Then it is slightly moved away. You can see the distance is increased. But in this case, what happens? Instead of putting this portion here, it has given extra support and it has been modified. It has been modified. So the wall thickness to the drilled hole should have a thickness equivalent to the thickness of the main body. What is the main body thickness? This is the main body. This is the main body, and thickness of the main body is this much. Same thickness is given to this body T. You can see T, and this one is also T, which is not shown. So this thickness is equal, and because of which what will happen, there will not be any crack formation or failure of the part. And the last point here is oval shaped holes. So oval shaped holes are often required. You cannot eliminate the requirement of this, and you cannot change it to circular. Okay, so what can you do? Should be oriented in such a way that the larger dimension of the hole is along the force direction. See, the force applied is here, horizontal, and the hole orientation is like this. Instead, change it to this. Change the orientation of the force such that it should be aligned with the point of application of the force, direction of the force. And the last point here is make provision for easy removal of the pattern from the mold. So I have learned this in casting that the pattern, generally the wood pattern or metal pattern, has to be removed, and when it is to be removed, you have to provide some clearance. So in that case, what you have to do is you have to provide a draft like this, that is inclined surface. You have to provide inclined surface so that the pattern can be easily removed from the mold. So these are the 9 points that you have to consider when you are designing the parts which are to be casted. So once again, design the parts such that it is in compression. Second is strengthen the part under tension by use of external device like this. Third is to round the corners. Shrinkage cavity should not be formed. Fourth is held uniform section thickness throughout. Fifth is avoid stress concentration. So change the design. Sixth is avoid thin sections. Then provide uniform wall thickness. Oval shape hole alignment should be such that force applied is along the larger dimension, and provide the clearance when you are removing the material from the mold from the sand. Okay, so these are the different points that are to be considered when you are designing the casting part. Factor of safety, also I had explained to you what is factor of safety, conditions, designation is also explained. So now I have to explain this properties of material. You studied this in strength of material, various properties of material.